The next thing that we need to know is about critical state. Critical state is a way of expressing, okay, of expressing the condition where uh, where does all substances are approximately the same state of molecular dispersion. Okay, so when some people, when they make an experiments initially, they found that at one point, which is the critical point, all substances, whether they are in gas or in the liquid phase, it cannot be distinguishable. Okay, it has similar properties. Consequently, the thermodynamic also should be similar, and this is where actually we call law of corresponding states, which express the idea that in the critical states, all substances should be behave alike. Okay, so I would like you to look at this graph, at these figures, and then I would like you to share with me your observation. Okay, when you start to see there is a container, when we have a piston here, okay, and then there is a water vapor inside the container itself, and we have the cylinder temperature, okay, which is the container temperature, is set to a specified value, that cylinder pressure is low enough for all the water to be vapor. So now you can think that, right, there is a water vapor inside this particular container, and then there is a piston which will be pushing through to compress the vapor so that this water vapor will become liquid. Okay, will become water in liquid. And experiments are repeated for different cylindrical temperature. So in this case, I would like you to have a look at the different run at different temperature. Okay, so here we have different temperature, okay, starting from 25, 100, 201 until 374.15 here. And then there is a pressure recorded when every time all this water vapor converted into liquid, which is mean that it is condensation pressure. So it recorded the condensation pressure. So you can see that at the temperature of 201.4, for example, the condensation pressure is 15.8. So the higher it is the temperature, so the higher it is the pressure that is required to condense the water vapor. Okay, but you can also start to observe that in the water vapor density and the liquid density of water is significantly different at low temperature. So here at 25 degrees Celsius, the water density is actually at the density of the water vapor is at 0.0234, while the liquid it is at 997, which is almost close to 1000 as we know earlier. But if you can see that when the temperature increases, the condensation pressure increases, and therefore you can start to see that here in the liquid density it started to reduce, while actually the vapor density is started to increase. Okay, so at one point you can see that at 374.15, okay, then you can start to see that the density of the water vapor and the density of water in liquid form is the same. So what happened next? After what happened to the 374.15, it shows here that there is no condensation occurs. So no condensation occurs beyond 374.15. And why is that? Because 374.15 is actually the critical points for water. So let's have a look at the phase diagram of water. Okay, so phase diagram is a type of chart used to show conditions at which thermodynamically distinct phases such as solid, liquid, or gaseous state occur and coexist at equilibrium. So here, you can see that at critical point, okay, at critical point where actually this is the critical point, and you have a temperature, okay. If let's say it is water, then this is supposed to be at 374.15, okay. And critical pressure, is also being given at corresponding temperature. So this is what we call as critical point. So whatever properties at this condition, the thermodynamic and properties, the phase cannot be validated. For example, is it in water or is it in vapor? We cannot distinguish that. Okay, and then at the same time, this is the density, the other properties are all the same between water and between liquid and vapor form. Okay, so the form is basically indistinguishable, right? So this is where actually, for example, the case that it is not very easy to use ideal gas equation. You cannot simply just use ideal gas equation for this scenario. So what does it mean by critical state? The critical state for the gas-liquid transition is a set of physical conditions at which the density and other properties of the liquid and vapor become identical. So this is what I meant with actually the graph that you have, okay? The graph that you have at one point, right? Then you'll be able to reach what we call as critical point here. Critical point is where actually the gas and liquid is the gas liquid transition having the same density and other properties. Okay, it is identical. And the highest temperature at which a species can coexist is called as critical temperature. Okay, and the corresponding pressure is termed its critical pressure. And what is means by supercritical fluid? It is a substance which is above its critical temperature and pressure. So let's have a look here at critical state for water. Okay, this is the phase diagram for water. So you have here, okay, at this particular point, right? This is what we call as critical point. So anything beyond this is what we call as supercritical fluid. Okay, supercritical water. Right. So at this particular temperature, this is what we call as TC, critical temperature, and this is the PC, which is the critical pressure. So if let's say we cannot use the ideal gas equation, so what suppose we use anyway? So this is where actually the next in the next slides that I'm going to share with you some of the virial equation of state in order for us to estimate the properties of the gas mixtures at the non-ideal condition.